Hi, my name is Antonio Trani, and welcome to a seminar on the runway exit design model and the landing event database. Now, I would like to make some room here for Ken Duffy at the FAA to make some introductory remarks.
Yeah, thanks, Tony, and thanks everyone for being here. Good afternoon. I'm Ken Duffy with the FAA's Office of Airports, and I'm the technical lead or the sponsor for this work, and along with my colleague Lauren Tagliano, who is from the Tech Center and helps us do all this interesting work with better tools and better data. And so this is a periodic update just on where we are with the runway exit model, kind of the current functionality and where we are looking to go. And part of the theme here really is that we have a lot of really interesting and useful data about aircraft operations that are occurring around the system, a lot more data than we used to have. And so a lot of the theme of this is being able to use that data in tools that allow for better airport planning and airport design. So anecdotally, it seems that we've, collectively, that from time to time, we've built high-speed exits and traditional exits in locations that really did not serve to reduce runway occupancy time as much as had been hoped. And so this tool is really about giving high confidence that the work, the necessary work that goes into building exit taxiways can really, we're going to build those exit taxiways in the right location. In terms of connecting that to our advisory circular guidance, in the new design AC, this is certainly referenced in the draft that came out for public comment, but it certainly continues into what would be the final design AC. We really emphasize the Redim, the runway exit tool here, as the preferred way to do analysis for exit taxiways and high-speed exits in particular. And one of the things you'll see coming forward is that when a high-speed exit initiative comes in, a project comes in, we're really going to want to see that it's been done in the current version of Redim to understand that there's some really robust data underlying that evaluation. I'm going to hand it back over to Tony, but that's kind of the setup of where we're looking to go from an FAA perspective and how we want to use these tools. We very much welcome your feedback and collaboration on them. We've put a good number of resources into this existing tool. There's work we still want to do, and so if you have ideas and suggestions as this moves forward, we very much welcome those. And Tony, back to you.
Okay, thank you, Ken. And thanks everybody for being here. Looks like we have 94 participants so far. So I think that as more people join in, I am recording the seminar in case somebody wants to look at this information, more carefully after the webinar is over. So hopefully nobody will object to that. And again, the hope here is to give you some useful information about the runway exit design tool and the landing event database that we have developed here with sponsorship from the FAA. And we are again very grateful to the FAA for that. I don't know, just by a show of hands, perhaps in the Zoom, since now we live in this new mode, how many of you have used any one of these two tools? I mean, I'm just curious to find out, how many of you are actually users of the tool. You can obviously raise your hand, just by clicking in Zoom. So it looks like we have some folks who have used the tool, but perhaps maybe I would say maybe 15% or something like that. So the purpose of the seminar here is to give you is really twofold: to engage you and to give us new ideas on how you want these tools to be developed in the future. And this project phase 2 goes up to the next year, so we have plenty of time to do that. But at the same time, I also want to present to you some of the the basic ideas of the tool, so that for those of you who are newcomers, you can obviously see what the tool is capable of doing, and to see whether or not this is the kind of you know uh, product that you may want to use. So here we are right now. I'm going to give you in the next few minutes explanations on the two tools that we have developed, and then we're going to talk about the new features. Some of these features are by design. Some features are just by almost by default, because we are collecting a lot of new data that has been collected, actually, that we are now processing for 4 more years of very high level, high definition data that comes from the airport systems that are detecting aircraft movements very, very precisely every second or so. First of all, I would like to acknowledge here that the project technical monitors Ken Duffy and Lauren Vitagliano really have been the brain behind this project here. This is a project that we have conducted through the National Center of Excellence for Aviation Operations Research next door to, and also special thanks to Tom Tessitor at the FAA Tech Center, who provided the data. And we also have 3 airports that we visited, that we were able to collect data and statistics to be able to validate some of the algorithms that we developed to detect when the planes are on the ground. So we went to Chicago, Charlotte, and also DCA. So these are the folks that need to be thanked for that. Ginger Evans, at that time, she was in the Chicago Department of Aviation, Jack Christine at Charlotte, and Jennifer Dermody at the Metropolitan Washington Airports Authority. So again, many thanks to them, because they allow us to really be able to do this. Once every time I will make them some just checks to make sure that everybody's hearing me okay. And let me tell you a little bit about the phases of this project. In phase 1, the objective was really to process all of these as the X data for 37 airports, years 2015, 2016, and then be able to use that data to develop a brand new version of the runway exit optimization model that we had originally developed back in 1994 for the FAA and for NASA. So this is a brand new version of the model. We call it Redim 3. And at the same time, it became evident that with all of this information, 37 airports, 2 years of data, you get around 11.8 million landing events. So we had to manage this data, and we created this landing event database, which now is accessible through a client program that you can download. And I'm going to give you some instructions or point to you where you can actually go there. Now, that was done in phase 1. In phase 2, which is where we are right now, we are basically processing additional data for 43 airports and 4 years, and years 2017 to 2020. So this gives us another wealth of information. Is probably going to be, as a minimum, another I would say 26 million landing events. So the total number of landing events by the time we put all this information together is going to be probably close to 40 million landings probably. And we are now in phase 2. Of course, we also want to improve the optimization model, the runway exit model, by perhaps adding a few features that were left in the previous effort, like pilot motivational practice, updates to the aircraft database, which we know is very important to some folks out there, especially new generation aircraft like Boeing 737 MAX and the Airbus A320neo class vehicles, and those are being added as we speak. We also, of course, we are going to have now or load the new information, which is another 4 years of data from 2017 to 2020. So the new model and the new landing database, we think, is going to be more robust, more flexible, and hopefully that will make life better for all the users. So let me first of all tell you what we did in phase 1. In phase 1, as I mentioned, we developed this landing event database, which is basically archives 11.8 million landing records across 37 airports that had ASDX data at that time. We developed a standalone product. Nick Hines is in the audience here. Nick is our senior research associate in the Air Transportation Lab, and he's really the brains behind the development of these two tools. I mean, so Nick is our really guru for the programming and a lot of the analysis that goes in. I also have to thank a lot of our grad students that have participated, Afshin, Navid. We also have Tim Leng, which is an undergrad student. So there are several people that, of course, I need to be mentioned because this is really a collective effort. So anyway, in the updated runway exit model Redim 3, we developed this Windows-based computer model, which obviously is a remake, completely a remake of the tool that we developed back in 1994. So right now, if you go to our website, which I will point out to you in the next slide, you can actually download version 3.09, which is this new release of the runway exit model, which has several improvements. We have a log there where you can see all the improvements that have been made in the last 8 or 9 releases. And the website is really the Air Transportation System Laboratory. If you, I am going to I should probably send this information via chat. So those of you who are able to do that, maybe you can just go directly to in the chat room. You can see there in the chat room that you have the information that we have there. And maybe I'll send it again because it looks like it copies some spurious word like yes there, which doesn't make any sense. So anyway, now you can see in the chat room there the actual web address there, and Nick has posted or is going to be posting this presentation as well, so that you can get this presentation right away and maybe you can revisit. We will be posting the recorded session later on once we develop that. That will probably be posted maybe tomorrow or something like that. Anybody has any questions or where we stand right now? And by the way, we want to make this seminar kind of interactive, so feel free to ask questions as I mentioned some of these tools, okay? Even though the program says that I was going to make the presentation, I'd rather you ask the questions as we are covering those screens. So let me just double check with my folks here. Tim, can you hear me okay? And you see the screen correctly?
Yeah, all good.
Okay, very good. So let's talk about the landing event database. If you have never used this, right now we are in version 1.24, which was released in April of this year. And the new features of this release are allows you to do queries by range, because when you have 2 years of data, maybe you are only interested in one particular month of the year. So now you are able to do those kind of queries by range. You enter a date range, and then you should be able to get only the statistics for that particular feature. We also added the statistics section that you can now basically just get reports for one particular runway or one runway exit. And this provides a very quick synopsis of operations by runway and runway exit. Now, the tool, as I mentioned, is now in version 1.24. And this is, again, the website where you can download the tool. The tool is a Windows application. It takes for you to actually be able to put this into your computer is probably around 95 or close to 100 megabytes for the client. And of course, what you are going to do is that once you have this installed in your computer, you're going to be basically connecting to a Amazon web server that we have here at Virginia Tech, so that you can actually use the tool. Obviously, 11.8 million records are not going to be installed in your machine. So what gets installed in the machine is the client that has all these windows where you can actually do queries, and you can do, you can learn what's going on at the airport there of analysis. So, before I tell you about the tool, let me just say that the tool requires a lot of background work that has to be done. For example, just because you have a lot of data, like 11.8 million landings, which is a lot of terabytes of data, 12 terabytes for 2 years, we had to collect very detailed characteristics of runway exit geometries, specifically around 3385 runway exits at 292 runways in the NAS. And this is important because when you look at the way we estimate what airplanes are using specific exits, we had to create these little traps or these polygons around every exit so that all of the airplanes that are going to be moving through that exit are going to be captured or trapped into that little rectangular area, and then we can verify that those airplanes are in fact using that particular runway exit. We also require to capture a lot of weather data because every 5 minutes we want to be able to provide, for example, wind, temperature, and other conditions when these landings are happening. And one more thing is that we went to these three airports that I mentioned earlier to be able to validate the algorithms that we use to detect touchdown location, because obviously in the ASDX radar data or the ASSC now, um, the vertical profile of the airplane sometimes varies, and we need to be able to estimate, when the plane is actually on the ground. Uh, my colleague Afshin Olamai has been doing a lot of the auditing effort. As you realize, now that we are going to have 43 airports instead of 37, well, not only means that we have to add 6 more airports. These are the airports in question here that we are adding with the new data from 2017 to 2020. But that means that we also have to audit all the other 37 airports because there have been potentially substantial changes to runway exits or thresholds, during the 4-year period between 2017 and 2020. So Afshin spent a lot of time. We have spent the last few months actually doing the runway auditing. This process is now complete, and certainly this is a good thing because right now we are, at the same time, we are processing the new data that we receive from the FAA. In order to validate some of these, we have to go to the field. We actually collected video data to be able to ascertain whether or not some milestones, for example, milestones on the runway, when the airplane touches down, whether it's with the main gear or the nose gear, whether or not those locations were estimated correctly. So as an example, this is a 737-800 landing, and you can see here, this is the velocity, the ground speed profile of the airplane, and this is the acceleration profile. You do have access to all of these profiles for those 11.8 million landings. But part of the story here was that we had to go to the field to collect some video data to make sure that these estimates that we have for touchdown location, whether it's the main gear or the nose gear, is actually accurate. And this is just an example of a table with some estimates that we did. So we went to Charlotte, Chicago O'Hare, and DCA to try to validate those algorithms. Now, the landing event database gives you a wealth of information, so we have created some ready-made query options. For example, the landing event database, if you look at the entire 2-year period right now, again, soon there will be 6 years total from 2015 to 2020. It provides you the aircraft mix by runway exit, things like that. Obviously, the runway occupancy time is very important. So we provide that in terms of distributions, like probability density functions or cumulative density functions, and you will see some examples of that. So we do have the speed profiles for the aircraft. For example, speeds at threshold, speeds when the nose gear touches down at the point of curvature as the plane starts making that curve, the runway exit, and then also at the runway edge and the whole bar. So we do have a series of metrics here. I'm not going to discuss every one of these, but I just want to give you that there's a lot of data behind the scenes here. Specifically, if you look at the raw data, which maybe I should go to the raw data right now. So I'm going to switch to the landing event database just to show you how this works. And I'm just going to do a quick check. Tim, can you see my screen here?
Yeah, I can see the screen.
Okay, so this is Atlanta. I just went to Atlanta Airport. This is the actual tool. And we are looking here at the landing for an Airbus A320 Delta Flight 1646. And you can see that all of these parameters in this table apply to this aircraft, right? So here we have the milestones, when the plane crosses the threshold, the touchdown location of the nose gear here, which is when we start noticing very high deceleration rates. And then we have the nominal speed, which is normally when the thrust reversers will be stowed, probably at 60 or 70 knots. And then you can see how the airplane is actually making the high-speed or the acute angle exit here at this particular runway. So if I pick another airplane here, you will notice that the conditions actually change because this is another Airbus A320. And it's very easy to navigate here. We can go to another runway, like say runway 10, for example, and we can say now we would like to only inspect 737s or 738s. Let's see if we can get several of those maybe. So I'm looking at 737s actually, and you can make the query here. Notice that you can do queries by range of dates. And now suddenly we have all of the data for all those 737-700s that were landing on runway 10. So now you can see again the same profile, runway occupancy time, all of these 30 parameters for every landing are listed here in the table. You can export these tables as comma delimited files if you like, and that's very easy because maybe some of you may want to use all that data in this particular format in other applications. So it's very easy once you install the tool to be able to do this kind of analysis, where you can export data. So for example, if some of you are involved in some study and you want to see the utilization of a high-speed exit or a regular right angle exit, you can very easily do that. And you can, again, with the landing event database, the raw data viewer, you can see all of these parameters very easily. So again, this is just what I was trying to explain to you interactively. Are there any questions about this so far? Again, feel free to, yeah.
I just wanted to mention that in addition to runway exit locations, this kind of data on where aircraft are exiting, it can be super useful for simulation, just in terms of populating that part of the database or the data set with the simulation tool about runway exit probabilities and real-world performance on the airport.
That's great, Ken. Thank you so much for that. And that is true. A lot of times in those fast time simulation models, like SimMod Pro or AirTop or RAMS or TAM, whichever is the model you guys use, you will notice that you do need that information, the probabilities, and also you can get good information on runway occupancy times if those models are able to take those as well, or for example exit speeds. So there is a wealth of information that the tool reports. For example, the panel here allows you to look at the actual speed profile for one individual landing. So you can do this for 11.8 million records right now, and then soon for many, many more millions of records that we will have there. This is the acceleration profile, or the deceleration. Notice in negative numbers in meters per second square. So this was for this Spirit Airlines Airbus A320 that I have selected here in the tool. So again, it's very easy to navigate. These days we added, the date range that you can query, and that makes life easier. For example, if you notice that there were some operational situations at the airport and you only care about the month of January of one particular year, then you can do that query by date. Perhaps what we think a lot of people may find useful for this tool is, of course, runway occupancy time, because remember, this tool was constitutes the database that we use to develop the runway exit model, because now the model is very data driven. So for example, here I have, I went to Boston, runway 4 right, and this is the cumulative density function of the runway occupancy time for this particular runway for all the aircraft. So in this case, these curves represent the CDF of all of the landings that happen in that particular runway for those 2 years. And one thing to notice here is that the runway occupancy time that we report out is going to be at the edge when the plane basically hits the imaginary plane of the runway. Normally would be the nose gear, because that's when we think the data that is being reported for the position of the aircraft happens to be always very close to the nose. I guess we verify that in some way using the video data. You can also report the fuselage out, which is right here. For this Airbus A380, that will be when the wingtip actually clears the imaginary plane of the runway, or we also report to the whole bar. There have been some folks who want us to report clearing the runway safety area. Typically, the whole bar here will be close to the safety area. Safety areas are normally for this class of aircraft 500 feet wide, but so that means 250 feet from the center line. Normally, hole bars are going to be 280 feet from the center line, so they are very close. So that could be for potentially one of the enhancements that we may be able to do when the plane reaches that RSA or when it clears completely the RSAs. Right? We have the geometry of the airplane, so we can actually estimate that as well. Right now, we only report these three events for ROT. When you look at the distribution of runway occupancy times, you notice that there's sometimes, bimodal distributions like this. This is for Denver Airport, runway 16 right. This is a very long runway. This runway is very long, and there's a high-speed exits located there, Delta 8 and Delta 5, for those of you who are familiar. But you can see clearly here that there is a dissimilar behavior between one high-speed exit and the other one, and that's because one of the exits is probably too close, and pilots are not really willing to use that because they let the plane roll, especially when they operate from a, with a high elevation airfield like Denver. So you can see very quickly here by looking at this tool, the kind of behaviors that you may perhaps find interesting at these airports, and maybe this gives you a clue that maybe this airport could benefit from another high-speed exit in between the two, between Delta 8 and Delta 5. I mean, that could be potentially one of the ideas. We also report the ground speed distribution. So here we have 5 ground speeds that are reported. I'm just showing 2 of them because in each one of these plots, you can actually zoom in and zoom out. So I was just interested in showing you the speed at the threshold. These are ground speeds, by the way, because we are taking this data from radar. And then this is going to be the touchdown speed that is estimated. These curves look awfully good. For those of you who study statistics, this will be almost like a perfect normal distribution. But this is actual data, so that means that we have a lot, thousands of landings of these airplanes, and actually that's where you realize that Gaussian distributions are pretty good. So in this case, we say 131 knots is the typical threshold crossing speed. Remember, ground speed for these Airbus A320s. If you are only interested in summaries, like for runway occupancy timetables, you can also do that. This is actually taken from the quick user guide of the landing event database. So you select the runway, you select what type of runway occupancy time metric do you want. Do you want fuselage out or to the whole bar? And then you just press query after you, of course, you have selected the runway that you want. And you are presented with this kind of nice summary table that shows you what are the ROTs for each one of the exits on that runway 8 left in Atlanta International Airport here. So you can see here that the values that are reported are going to be the ROTs, the average ROT for every airplane, every exit, and the percentage of the airplanes that are exiting each one of those runway exits. So we think that this is very useful information to get a very quick snapshot on how your facility is being operated. Let me stop here just to see if there's any questions about any of these.
I have one particular question. It's in regards to the ROT to whole bar times.
Yep.
So the question I have is, so for high altitude airports, does that ROT to whole bar account for the elevation adjustment for the whole bar itself, or is it just a standard whole bar distance for the category of aircraft?
No, it actually accounts for the high elevation airfield because the whole bar location is one of the parameters that we identify when we do the auditing of the runway exit. So if the whole bar, let's say in Denver, let's say on this runway, happens to be, say, 280 plus the adjustment, 1 foot for every 100 feet or so, then if that whole bar happens to be at 300 feet, from the runway center line, I'm just making a number, then that will be reflected in the database, in the ROT. Because we physically went to the using Google Earth, and we actually measure where the whole bar is. Because we have to actually characterize several, we will describe this a little bit later, but we describe 3 or 4 important parameters, geometric parameters of the runway exit, in order to be able to ascertain when the plane has reached that point. Yeah, so we are not just taking a whole bar without adjusting it for altitude. We do, because that is part of the measurements that we do.
Perfect. Thank you for the explanation.
Yeah, no problem. Now, if you want to see the snapshot of the speed profiles, again, for an Airbus A319 landing on runway 19, you can obviously select the airport, and then this kind of profile will be generated. Now, notice here there are thousands of landings, of course, on this runway 19 for Airbus A319s, but you can clearly identify as a function of distance here where these airplanes are taking those exits. So in this case, maybe we identify probably 5 exit locations, maybe 6. This is probably the end of the runway. But you can see here the speed profiles, again, keeping in mind that this is ground speed. So when you have a very strong headwind, these A319 may be landing at 110 knots. Whereas when you have maybe a little bit of a tailwind, you may be landing at closer to 140. Now, of course, there's always pilot variations there as well. Now, the tool can be used easily to identify, again, some useful metrics of ROT. Like, for example, in this case, we went to O'Hare, runway 9 left, which is the northernmost runway. It's only 2 usable exits here. And you can see that by using the tool, I can identify not only the aircraft fleet mix that lands on that runway, but also the CDF, or the runway occupancy time cumulative density function. Again, the 3 values being reported there. So you can identify what's the 50 percentile, the 95 percentile. You can see 71 seconds. That's pretty high because, again, there's only 2 exits, that are usable here. This runway, by the way, is only 7,500 feet long. Now, if I go to another runway at O'Hare, 27 left here, is a little bit longer runway, but has a lot more exits. You can see that now the 95 percentile value has dropped to about 64 seconds. So again, for a given facility, you can very easily migrate or identify what sort of performance you can get out of the runway exits that you have at your facility or at your airport. And also, of course, you get to know exactly the aircraft fleet mix. This fleet mix not only is reported in pie chart, but you also get a table on the right-hand side of that pie chart that is reported by the model. We do have a quick user guide that we have put together. So the user guide gives you this step-by-step approach. And again, the user guide can be found in the same website that we gave you at the beginning. So, when you go to the Air Transportation Lab, you should be able to, I'm going to go back to this, you should be able to get the documentation there, the installer, as well as a quick user guide that we call it user manual for the landing event database. And again, I would encourage you to go to that website. There was a question here about the dry and wet. How weather is considering the effect of runway occupancy times? Mason is asking that question. Well, the weather, remember, we are capturing weather information from this from the weather sensors, I guess, at these airports, typically every 5 or every minute that is being reported. However, what we are basically reporting, unfortunately, we don't have data that tells us, for example, if the runway was really wet or was it dry. So in some way, that is one of the gaps that we see in this landing event database, that if we have, for example, better capability to identify when the weather phenomena was wet or dry with the runway, actually, because, the weather information that we may get is a rainfall rate, but that doesn't mean, if it happened 30 minutes early, we don't know if the runway is still wet, for example. So that piece is still uncertain. So I think that that's a very good question about dry and wet conditions. And, for the runway exit model, we suggest that users use probably a 10-90 ratio, 10-90%, 10% wet, 90% dry, based on typical cities that we have identified in the US, where we have identified that kind of ratio between when the runways were wet or were potentially dry. But in this tool, it's very difficult to identify that because the way the information is being reported is only a string, and we don't really know if the runway is actually wet or dry at the time of the landing. So that could be if any of you at the FAA has that kind of information, that would be extremely useful, I think, for this kind of tool, really. I mean, that could be one of the potential enhancements, and that's why we are talking to you all the time here. I'm going to give you, yeah, go ahead.
Tony, I appreciate that comment, and we've looked around that for that a few times. Really, I mean, we know when the runway is wet, and it really gets into an interesting question, the evaporation rates, and at what point you can consider it dry. I suspect in hunting around, if anyone on the call has some data on that, please share it. But in searching around within the FAA, we've not been able to find that at this point, and I suspect it's going to be a research task that we look at to find a better way to be able to calculate that parameter.
Hey Ken, Ray Z, local ATAR not available, or that was based on?
So that gives us the precipitation, and the precipitation occurred, but it doesn't tell us how quickly the runway evaporates after the rain ends, for example.
I don't know the extent, but the Talpa NoteCam data may give you some clue.
Yeah, and we looked a little bit at that too, and I think it's really pulling some of that Talpa NOTAM data in terms of when it's reported dry, but also with some field observations to really fine tune it.
Okay, great. So these are, I think, Ralph, you made a comment about the importance of ROT for evaluating the throughput of the runway. ATC only needs the aircraft to exit the runway to continue the clearance. So there is not much value in evaluating ROT to the whole line. The whole line actually was added later because there were some folks in Europe that apparently they use the ICAO definition for ROT, where apparently ICAO thinks that the runway occupancy time should be measured all the way up to the whole line. At least that's what they told us. And since we had the trajectory of the aircraft all the way up to the whole bar, and we identified the whole bar for other purposes, then it was added there. So I just wanted to mention what was the reason for adding that. So let me just give you in a few minutes, a little bit of what we have done with the runway exit design tool, Redim 3. Right now we are in version 3.09. You can download the model here from this particular website, which is the Air Transportation Lab. And in this particular model, what's going to happen here is that this one requires a little bit more hard drive in your machine. It's about 1.8 gigabytes of hard disk space because there is a lot of data that the model needs to install. This is a fully standalone application. You are not connecting to a database like in the landing event database that you are connecting remotely to a server. So this is a standalone Windows application, and that's the reason why the requirements here are a little bit more, probably more realistic, I would say. But anyway, most of the machines should be fine running this kind of model, whether you have an Intel i5 or an Intel i7 or i9 processor. I run this model in my Mac using Parallels, and it actually runs very well. So, the model should be able to run in most machines. The model has basically three types of analysis, an evaluation mode, an improvement mode, and a design of optimal location mode. So if you are designing a brand new runway from scratch, you could use mode for the design optimal location mode. But the suspicion is that most of the users of this model will probably use the evaluation and the improvement mode, where you can evaluate an existing runway, get the benchmark, and then you can say, what if I add or delete or get rid of maybe some right angle exit and start adding acute angle exits? What sort of improvement am I going to be able to see? So that's kind of the synergy of how this may work. Now, in terms of the workflow for this tool, you need to have the runway exit locations and the geometry. Here we use Philadelphia as an example. And then the model has basically 5 steps that you are going to be taken over. The model takes you through 5 steps to populate information. You obviously need to find, to supply where the runway exit locations are, what kind of exits are these. You need to supply the aircraft fleet mix. And then, of course, the model, once the model runs, the model will give you a runway occupancy time table as well as a lot of different tables and plots. The model is basically a Monte Carlo simulation tool that takes the data that we gather in the landing event database. We developed a lot of kernel distributions for individual aircraft. 290, close to 300 airplanes are in the database right now for their model. And then it runs thousands of landings for that particular individual aircraft, and then it collects information about what exits that model or that vehicle is going to use. So it reports data by individual aircraft types, as you see here. This is an example for Philadelphia 27 left, where you would find out, small regional jets like the CRJ2, all the way up to Airbus A330, 300. So the outputs of this model are going to be, of course, the runway occupancy time, fuselage out or whole bar, both of them are available now. The ROT, weighted average runway occupancy time, the standard deviation that could be very important because it's not only good for us to know what is the weighted average runway occupancy time, but also if the standard deviation is high, then controllers may have more difficulty reliably, separating the aircraft and then perhaps reducing those intra-separations. So you also get the individual landing roll times for every one of the simulated landings in your run. Typically, there might be 50,000 landings per aircraft. So if you have 20 airplanes, you get like 1 million rows, of output in the model. And you can easily export that to Excel or maybe a database, because Excel will probably only read the first 1 million lines. But anyway, you can export that to some other applications where you might want to be able to massage the data. You get, of course, a table with runway exit utilization, and then you also get the individual landing performance. Let me see if I can quickly switch to the model here, just to show you how this model looks like. So here I had made a run, for example. So the model, gives you graphical output. In this case, I have the different exits that I programmed here. I have a bunch of exits. I have a lot of airplanes. And then it gives you a graphical depiction of what exits are being used by each one of those airplanes. Now, if this is not a good plot because maybe you have a lot of airplanes like shown here, you can still get tabular details about the runway occupancy time by exit and by aircraft type. And you can see here how the runway occupancy time tends to increase as the exits are moved downrange, on a given runway. So somebody else, Andy, says that ROT to the whole line may actually help with taxiway flow. We agree, so maybe that's something that you guys can also use. The runway exit locations and the aircraft fleet mix is something that you defined. In the model, again, we have about 290 plus airplanes in the database. So you can basically just select among all of these airplanes that we have here. And again, this database is basically compiled as a summary from the landing event database. So these two models are connected by that feature. The landing event database is all the raw data that we use to be able to calibrate the behavior of this model. And I'm going to tell you very briefly here, how this model actually works. So let me go back to the full screen here so that everybody can see the screen. So the situation here, those of you who use the old model, the Redim 2.1, that was an old model where we had to even program the fonts because at that time we had no Windows. So anyway, if you have used that model, there are a lot of differences between this model and this model now. This model, Redim 3, is very data-driven. And all of the data is there for every individual aircraft type, 298 aircraft model versus 5 that were modeled directly in Redim 2.1. Now, 2.1 also had about 70 aircraft that were modeled indirectly, but obviously we are very happy to see that after collecting 2 years of data, we were able to get about 298 airplanes, in the data base. New airplanes, by the way, are coming very soon. As we are parsing or processing the new data, we have about 28 to 30 airplanes that have been identified as new airplanes, and I think I have a graphic on the next slide for that. So right now the model has 134 turbofan aircraft, 105 piston, and 59 turboprop. But the good news is that now that we are expanding the data to include information at 43 airports from years 2017 to 2020, right now these are the airplanes that are being added to the mix. So in the Class B aircraft approach speed B, we have airplanes like the Pilatus PC-24, the Cirrus Vision, a few others, like the Citations, and also the Global Express and the Dassault Falcon 8. But then perhaps more important for many of you, we're going to have a lot of airplanes that are new generation aircraft, like all the Neos and the Maxes there, as well as the second generation of the Embraer aircraft as well. Gulfstream 500, 600 are there, and then in the Class D, we're going to have the 737-8 Max, Dash 9 Max, and then you will have the two versions of these. I guess these are in flight testing, so these guys are probably showing up probably in Seattle. That's maybe where the new data is going to show up. But 787-10, and then you have the Airbus A330, the new versions of that, as well as the 350-1000. So these are going to be, somebody's asking about the Airbus 220. I think that airplane is going to be there. I think I forgot to add it to the list here. That should be there as well. So thank you, Bob, for reminding us that. It should be there because Delta has been using that airplane for some time, and some of the other airlines probably fly that airplane as well. So that should be part of the C group. And maybe I'll go ahead and add it or amend this presentation a little bit. Now, the model, it uses a menu structure where you typically move from the left to the right. And as I mentioned, I'm not going to make you an expert in running this model, but right now we will have actually a webinar that we are going to be recording in the use of these two tools more extensively, and we will be posting those probably this summer as well. And if there is interest, we can create like a 2-hour webinar as well. Yeah, somebody says that it will show up as a C100. We agree with that, either the C100 or the C130. That's for the Airbus the 220. So anyway, the model has this graphical as well as tabular format to be able to report the data. And at the end of the day, what this model allows you to do is to design, to prototype how a runway may actually operate in the future, where you start adding additional runway exits, for example, or if you are doing some improvements to that facility. I mean, that's the whole idea. The model has a navigational panel here that shows you all of the scenarios that you run. This is just a screen capture that I did of my hard drive. And again, I'm running this on a Mac using Parallels. It runs very well. And, sometimes if you put 30 airplanes and you put 20 exits, yes, the runs may take a few minutes, but it's not unreasonable. Probably in 3 or 4 minutes, you get the answer if you have a fast processor. So anyway, you can see that the model will, after you make the run, you will be able to see all of the inputs that went into the model and all of the outputs as well. Runway settings, exit locations, runway occupancy times in tabular or in plot form, etc. So again, that's what I was trying to show you here when I was going to when I was trying to show you the model here, that for each one of these scenarios, you can get a wealth of information. For example, I can get a plot of the runway occupancy time for every exit, for every aircraft. Now, this plot is probably less useful compared to the table. So I always like to see the table, because in the table, I can actually, export the table. You can save the table as a CSV file, and then you can bring this to Excel, and maybe you can make a nicer presentation to your client or, to whoever you are trying to present this information to. So the panel on the left here allows you to manage the scenarios that you create in this particular tool. Um, some people, Nick is saying that it shows as BCS3. That's for the Airbus A3, the 220. So we will have the 220 there. I can guarantee you that. So don't worry. That's why I said between 20 and 28 and 30 airplanes, because I was not. I said maybe I should add two more just in case. But by the way, we don't know exactly until we process all the data, because if some airplanes do not have enough data, we may actually throw them out, because if you don't have enough distributions or data to create those distributions, it will be a little bit difficult to ascertain how that vehicle moves. Now, overall, what we are doing in Redim is basically creating a profile. Every landing is going to have these little faces here. For example, the airtime, the plane touches down in the main gear, the nose gear. The pilot, brakes nominally at some deceleration rate. Obviously, this varies according to the runway length and according to the motivational practices. And then eventually, we either put the runway occupancy time all the way up to the fuselage out, or to the speed when the speed of the whole bar has been reached. A lot of times airplanes actually may stop there. But the model uses the same kinematic equations that we use in Redim 2.1. So each one of these phases is broken down into some fundamental equations of motion, so that we can calculate how much time and how much distance the airplane has traversed. The blue dots here happen to be landings collected at one of the runways at Chicago O'Hare, just to show you that the profiles can be, again, this is the data from the landing event database, and the profile shown here is what Redim 3 will try to do. Now, the model is Monte Carlo simulation, so it will give you 50,000 different landing profiles for every airplane that you model once you run the model. And the other thing that is important to capture about this model is that now it's all data driven. So for example, one of the important characteristics that we found in this analysis by collecting all this data and analyzing it is that the behavior of the aircraft is heavily tied to the runway cluster, to the runway length, among other things. These are 20 clusters that we currently have in the model, and since we have about a pool of 292 runways total, that gives you an idea how many runways were actually put in each cluster. So the clusters, notice here, start with a very short runway. We have runways as short as 2,800 feet, maybe. Some of those at Boston, for example, I think is runway 23 right. And then we have very long runways, like Denver International Airport. It's only two of them. So here, that's two runway ends, by the way. So that's why there's a 2 there, but there's really only one 16,000-foot runway there. And each one of these clusters changes the behavior of how the airplane is going to perform on the runway. For example, let's look at an Airbus A320 here, and these 20 clusters. If you probably don't recall, but let's say cluster 11 is a very short runway here, about 5,500 feet. When you have an Airbus 320 landing there, according to the database and the analysis that we have done, the mean deceleration rate is very, very high, negative 2.72 meters per second square. When you are landing the same aircraft on a long runway on cluster 2 is that cluster here where the runway goes from 13,000 to 13.5, you can see that the deceleration rate is pretty obvious, that it's going to be very low compared to the short runway. So these distributions is what drives the model behind. So when you land an Airbus A320 on a given runway for a given runway length, each one of these clusters will get fired up in the Monte Carlo simulation, and then we will try to do the analysis based on those. To illustrate the point, let me take the median points of the deceleration rates for some of these clusters. And this is for an Airbus A320, and this is for a equivalent 737-800. And you can see here that if you were to make a plot of runway length versus deceleration rate, you can see that there is a well-observed profile here. Obviously, the clusters, I took the mean values. And remember, there's many runways that belong to each cluster here. So I'm just taking the average deceleration rate for those. So here, the point is to illustrate that when you have a long runway, in general, the deceleration rates are going to be observed to be low, because pilots do not want to brake very hard. That reduces maintenance and saves the brakes. Whereas if you are landing at SNA on a 737-800, you're going to have to brake hard because the runway is fairly short. So this is just to show you how the cluster affects the landing roll profile performance of these airplanes. And we have these clusters for each one of those 298 airplanes, okay? Similarly, we observe touchdown locations. The touchdown location, when you have a long runway, the pilot has more leeway that maybe I can land long, right? So when you look at the 12,000-foot runway here for an Airbus A320, according to this profile here, if we were to take the average of all these clusters, the touchdown location for the nose gear would be probably around 820 meters, whereas on a short runway, it's going to be very close to the aiming markers because the pilot wants to get there quickly and make sure that you can decelerate the aircraft with the remaining runway. So again, these are some of the things that we are start noticing on how the model works. One more thing is that the behavior on the runway exit is also driven by clustering technique. So 3 parameters that define a runway cluster are the radius, or the equivalent radius, the path length, which is the length from the point of curvature all the way up to the whole bar, and the exit angle. So we notice when we do this cluster analysis that these are the key ingredients to make the cluster. And for example, just to illustrate this, we have 20 clusters. I'm not going to show you the 20 here, but you can see that each cluster is going to have its own angle, radius, and path length. And basically, this is just an indicator that tells you the kind of exit this is. And the point that I'm trying to make here is that even though you may have, let's say, acute angle exits, you may have actually 2 clusters for that, cluster 2 and 6 here. You notice that in one case, I have a 30-degree angle, but I have a very short path length. So for whatever reason, we have a short path length here all the way up to the whole bar. Maybe because there is a runway, a taxiway that is close to this runway. That could be the case of Newark. Some of the runways there may have only 400 feet between the runway center line and the taxiway center line. So in that case, the path length may be a little bit shorter. Some runways, by the way, I'm not just trying to say Newark, but there might be others where the angle is kind of weird. Sometimes it's between 30 and 35 or something, and you may have a short path length. The point of that clustering analysis is that when you have a runway with a long path length, like cluster 6, which is probably a typical standard acute angle exit with radius of 1,500 or 1,800 feet, like in the old standard, you see the path length here, right there, much bigger than the path length on cluster 2. What happens is that based on the landing event database that we observe, the speeds, the exit speeds at the PC points in cluster 6 are going to be substantially higher than the exit speeds at cluster 2, because the cluster 2 is a very short, even though it's presumably a 30-degree angle exit, nevertheless the pilot is not very confident because they know that they have to decelerate quickly before they reach traffic, maybe here or the whole bar. There is a question, how does the model adjust the cluster indicated? Let's see, Nick is actually answering those. So thank you, Nick, for doing that. I'm new, I guess, to chat rooms, so maybe a lot of times I'm very slow here. But anyway, I'm just trying to give you a story here that the model is very data-driven. So if you want airplanes to exit quickly, on a runway, you're going to have to define a nice path so that your runway exit belongs to that particular cluster. This is very different than the previous model, because in the previous model, I could have a runway exit and I could say I want airplanes to exit at 65 knots. And maybe geometrically, the runway exit was not prepared for that. In the model right now, you are limited to what has been observed. In other words, we do not want to give a false hope when you design a new high-speed exit that all the time pilots are going to take those exits at 60 knots, if that happened to be the design speed of the exit. As you can see here in cluster 6, these are fairly good speeds actually for those high-speed exits. And these are observed values, and this is what the Redim model is trying to replicate. Okay, so finally here, the Monte Carlo simulation is basically taking all of those distributions that we had, that we mentioned for approach speed, mean touchdown location, deceleration rate, etc. And he's doing this profile 50,000 times for every airplane. And then after we do this, and remember, for every airplane, that means if you have 20 airplanes, you will get a fairly large output file, and that's okay because the more data you have is probably the better. And then the model will report the information in tabular form, which means it will give you each one of these characteristics. Like, for example, how much time the airplane took from crossing the threshold all the way up to the touchdown point or the nose gear touchdown point, etc. What was the time here? What was the distance? So you get a wealth of information, and then all of these tables can be exported or saved as comma-separated files, that you can then analyze in other applications as well. So this is just a very quick overview to show you how this model actually works. So this model is, again, very data-driven and is very heavily tied to the observed behavior that we have from the landing event database. We are obviously going to do improvements to this model, and one of the reasons we would like to hear from you, whether it's today or when you have some time to think about this, is to send us feedback on what would you like to see in this model. So, but please wait until the end of the presentation because we have some things to tell you about the things that we are obviously planning to do as well. So let me stop here just to see if there's any questions in general about the Redim model or the landing event database. So far, so good. Okay, just a quick review of some examples of the type of application that we have used this model. In the previous effort, in phase 1, we actually applied this model to 4 examples or 4 studies that we did for these airports: Philadelphia, MKC, Boston, and Denver. And I'm just going to focus on Philadelphia because I think it's easy to be able to explain what happened here. Part of the study here is, basically you have a runway there, and there is a need that maybe controllers or pilots said it would be nice if we can have another exit out there in this particular runway, 27 left. So the idea here is that you use this model to be able to run several scenarios, and we run one scenario with one high-speed exit with 10% wet conditions and 90% dry, and then we also rerun the same scenario for 20% wet and 80% dry. And these are the locations, the optimal locations that the model gave us for that particular situation. Now, of course, when you create a new acute angle exit, that may require that you close some of the existing or you replace some of the existing exits there. So the first thing we do is just, collect the fleet mix from the airport, including some corporate jets that operate there, like the Bombardier CL, the Challenger 300 and the Cessna Citation 560 XL. All the other ones are normally commercial airplanes there, including some cargo planes like the MD-11. And this is the situation. We have the original runway here, and there is an identified need that maybe we can substitute Sierra 9, which is one of the right angle exits, for another high-speed exit because that would be probably preferred. Turns out that Sierra 7 probably is too close to the threshold. When that threshold gets displaced, this runway exit is probably not very usable for most of the airplanes because the PC is located only at 3350. So the idea is that you prototype in the model, you let the model decide for an optimal location between these two, closing some of these exits, which you can do in the model by selecting close. There is a little radio button to be able to do that. And then the model says, I found 2 good exits for each one of those scenarios, okay? Well, actually one for each scenario. 5190 feet from the threshold and 5280 for the case where we apply 20% wet and 80% dry. And then what we do now is, let's go back to the original geometry here. And, we study, obviously, there will be a lot of factors or where you put these high-speed exits ultimately. But in this case, we say, well, maybe the 2080 scenario provides a better location because that makes the pavement overlap to be minimal here compared to the other one. Remember, the other exit was at 5190, So that will be closer to the right here, and there will be more pavement overlap, which may not be a desired outcome, by the way, under the new guidance that the FAA has in the advisory circular. So anyway, if this happens to be the location, then you say, well, how much benefit do I get by putting one high-speed exit at 59 or 5,280 feet? And this is where the model is going to tell you the story. So the baseline run gives a weighted average runway occupancy time of 52 seconds, 52.3. And then we notice here that you are reducing the weighted average ROT by about 4.4. In this case, this is actually more optimal than this, but if you want to reduce the pavement overlap, the disbenefit here is only zero point 0.2 seconds, so it's not a big deal. So maybe this is a better choice. If that, it's kind of always a trade-off in the design. So what the model is now doing is giving you the opportunity to judge what will happen in the future if that high-speed exit replaces Sierra 9 or that right angle exit. And then you can actually inspect the runway occupancy times for individual airplanes to understand, what is the actual benefit that each one of these airplanes is getting from that new location. In this case, the new high-speed exit at 5,280 feet, the green bars are going to give you the runway occupancy times, the average for individual aircraft types, whereas the existing high-speed exit at 6,073 will be the value in the red bars. So again, this is just an example of how you use. No high-speed exits in multi-node intersections. Michael, you are correct. That's why we said that maybe, something is going to have to give in here, right? We don't know if this is a desired output. The model is only judging the location of the exit based on the minimization of the weighted runway occupancy time, but certainly it's up to the designer to judge whether or not those locations are going to be acceptable due to some specific design criteria, as you mentioned, the multi-node intersection case. So we agree completely with that, and that's why this tool is only a guidance tool, really, but it's up to the designer to decide ultimately whether or not that needs to be built there or not. And the nice thing about having a model like this is that you can always offset the location to avoid those multi-node intersections and then see whether or not you're still able to get some benefit out of that. I think somebody wanted to say something. Please go ahead.
Hey, Tony, it's Ken. If you go back to slide 58, I wanted to kind of elaborate on one further point here. So part of what we talked about is really having confidence that a given runway exit location, with a new project, is really going to have a meaningful benefit in terms of runway occupancy time. And certainly you could have an example where perhaps the runway occupancy time goes from 60 seconds weighted average to 58 seconds. And certainly that's a benefit, but it's not really a significant benefit. In this case, it's a difference of 52 seconds down to about 48 seconds. And that crosses a really significant barrier, which is the 50-second weighted average runway occupancy time point. And below that 50 seconds, then the runway becomes, it's possible for the runway to become a 2.5-mile separation, arrival to arrival runway versus the standard 3-mile separation. And that's really a change where you would expect a change in the call rate and a more meaningful improvement in throughput capacity of runway. So this is a really good example of where the calculations can help us to have confidence that an improvement would actually result in that runway occupancy time and capacity improvement. And this particular histogram you said left in Philadelphia is that it's a runway that is not currently authorized for 2.5-mile separation, and both controllers and the airlines there were interested in pursuing that. And this is kind of data that gives both the airport and the airlines, but also the FAA, confidence that the project could really be successful.
That's a great, Yeah, that's a good point, Kent. And one more thing I wanted to also say is that when you get the detailed output from the model, I did not include this plot in the presentation here for brevity, but you can also plot the standard deviation of the runway occupancy time. And the standard deviation gives you another important metric, which is, if you notice that the standard deviation is very high, controllers may not have as much confidence as bringing down the separation to 2.5 nautical miles, right? As Ken mentioned, the 50-second threshold is important. But the other thing I wanted to mention also is that you can inspect the reductions in the standard deviation of runway occupancy time, and those could be quite significant as well. So that means that most of the airplanes are going to be contained within a runway occupancy time, and you don't have to worry about airplanes, staying on the runway sometimes and potentially disrupting the operation as much. So that's a good point. Um, the typical use of the model, I mean, there could be numerous reasons why people may want to use this model. I mean, these are just kind of standard workflow that we use in our lab. You run the Redim model, you get runway occupancy time, you feed that into a capacity model, as Ken was mentioning. When that threshold is now, is improved down to 50 seconds, maybe this model is intelligent enough to start applying reduce intrail separations to 2.5 miles, or maybe you want to do an analysis of a wake recat 2 situation. This is just an example of a model that we have in the lab, runway capacity that we developed for the FAA and NASA. And you may be able to see some potential capacity gains there. But some people may prefer just to take the output of this model, create these distributions, and then feed those into a fast time airport simulation model like RAMS or SimMod Pro or AirTop or TAM. Whichever models you guys are using, you may be able to feed the output of the Redim model into these models, because most of the time these modelers use very generic parameters for the deceleration rate and for the runway exit uh, you know, uh, capabilities that these airplanes are going to exhibit. So we think that this model is a good complement to some of these fast time simulation models. At the end of the day, part of the story here is that as we push towards reduced intrail separations in the NAS, obviously the challenge here is to also make sure that we can contain the runway occupancy time. So with the output of this kind of model, you may be able to start thinking, well, that if I start reducing intrail separations down to 2 miles in the future under RICA 2, that starts pushing the envelope here in terms of the typical separation. That will be about 54 seconds in the air between two Class 737-800 vehicles. If you added the buffers, which have been characterized, I mean, at least we have measured those to be between 16 and 19 seconds, you can see that suddenly the runway occupancy time becomes a more important parameter in the future when we start pushing these intrail separations to be shorter or closer to each other. So in order to be able to guarantee that we are going to be able to meet this requirement of reduced intrail separation, ROT becomes an important consideration. So these are just two examples of the types of things that we typically do in the lab. Now, let me tell you something about the new features of the model. We realized in phase one that pilot motivational practice is very important. We did not include that in the model because we were trying to develop a good first version of the model, and then we said maybe that could be developed later. One of my colleagues, Navid Mirmo, who now works for American Airlines, he was my PhD student, and he developed some algorithms that we are now going to try to improve. And Afshin Olamai, who is also in the call, is another grad student here at Virginia Tech that is going to be working in pilot motivational practice. So this is an important consideration that we think for the model, because then in the future you will be able to specify what airplanes may be eligible for pilot motivation, and then the model will be able to adapt. And I'm going to give you an example of that. We also will have an expanded aircraft database, of course. We have either 28 or 30 airplanes, and again, this remains to be seen because we have 4 years of new data So that gives us substantial information that may actually push the number of new airplanes even higher than 30 potentially. And we will have, we think we will have improved algorithms to predict runway exit use for small single engine airplanes, which right now are not very well represented in the model. So those are going to be some of the things that we would like to do. In terms of the motivational practice, this is important because right now the model takes a runway cluster and says all of the landings of that class of airplane, as I mentioned to you in the example I was giving you with the Airbus A320, are going to perform kind of similar in that cluster, right? But now we are going to be adding a motivational factor. So for example, if 737-700s landing on runway 24 right in Los Angeles are heavily motivated because maybe they belong to an airline whose gates are located, far away. If you were to roll down range of the runway too far, then you may be able to specify in a qualitative way the motivational factor. This will be similar to what the pilot does when they program the auto brake system when they land on a runway. If they want to really brake hard, they're going to put the auto brake in the high mode, right? So in this case, we will have, the nominal profile for a 737 will look like this. But if I flip the switch and I say I want high motivation for that airplane, now the blue area here of this distribution is going to be triggered and is going to be used most of the time for that class of aircraft. Now, you still have to define two parameters: what airplanes are eligible for this practice, and also what percent of the population, because we realize that not all the 737s, 700s landing on that runway are going to be motivated. Some belong to airlines that want to go all the way up to the end of the runway, maybe to be able to get closer to their gates. So this is going to be something that we are currently tinkering with, the idea of this algorithm. So you will have different profiles, even though these guys are applied to the same cluster, in this case a long runway, let's say at Los Angeles, like this is a 9,000 foot runway, 24 right, then there will be, when you flip the switch or high motivation, then this new CDF will be created. So the kernel distribution that belongs to that cluster now is going to have subclusters, so to speak, and then we will be able to guide the model to start braking a little bit harder for this class of aircraft, simply because you as the user, maybe you understand that there are some vehicles that are going to be applying this auto brake or high motivation mode simply because they want to get to their gates faster. Remember, in this analysis, we do have the location of the pseudo location of the gates, so we know presumably what is the percent of these operations that potentially are using high motivation, moderate motivation, and low motivation, as we may call it. I mean, these are just generic names that we are giving them right now. So somebody, Ralph, is asking, given that both temperature and fleet mix can vary with season, is it advisable to use seasonal variations to see the results are consistent throughout the year? Yeah, I mean, certainly you can run the model and you can change the fleet mix, and the fleet mix will be probably the only big change that you can make. Now, in terms of the temperature, I mean, the model, we have functions where the vehicle is able to fly faster if you are landing at a high elevation airfield. So we make those corrections. For temperature, right now, we also put temperature in the model as an input. So if you put a very high temperature, automatically the model will adjust the approach speeds to reflect faster approach speeds, when you have a hot day. So that is something that is already available in the model, Ralph. I don't know if I answered the question correctly, but I'm just reading here the chat. So anyway, the pilot motivation is important. On the other spectrum, on the other side of the spectrum, we are also planning to improve the small aircraft runway exit. This is an issue with the data, really, because this particular data that comes from the big 37 airports may not have a lot of information about small airplanes, or if it does, then those small airplanes like single-engine piston-powered aircraft may exhibit behavior which is highly anomalous. For example, a Cessna 172, you see all these dots here. This is work that Tim Link Letian is actually doing in our lab. He's an undergraduate in aerospace engineering, and he's in the call right now. So thank you to Tim for this work. And what we have observed is that, when Cessna 172s land even on a short runway at SNA, for example, they exhibit behavior which is very different what the pilot operating handbook tells us. Right? These lines here are the POH, and this is kind of the model that depicts all of these blue data points that are reflecting deceleration rates for that Cessna 172. We want to improve this in the model because we want this model to be able to not only apply to larger commercial aircraft or those that go from class AAC, B, all the way up to D. So right now in the guidance that we give in the quick guidance for the use of the model, we suggest that if you are planning to use general aviation aircraft, you should probably use airplanes that have a little bit higher performance like the Bonanza 836 and the Piper 34, because these airplanes, once you start reaching a threshold of approach speeds for these airplanes that have higher performance, in general, Redim will be okay. But for airplanes like the Cessna 172 right now, the model, based on behavior that is observed in the landing event database, the model thinks that these airplanes are not going to be able to brake very hard because these airplanes are not really motivated to brake hard when you land on a long runways, right? Which is most of the cases that we currently have when we capture the data. So anyway, that's another improvement that we are currently doing in the model. In the features of the landing event database, obviously we're going to have 43 airports now versus 37, and I listed the new airports in another slide early on. We will have between 28 to 30 new airplanes, including the Neos and the Maxes, as well as some things that we have observed out there. And again, this table is the same table that I listed before, so it's missing the Airbus 220. My apologies for that. It will be there. And of course, the other feature is that a lot of the runway exits have been modified, even minutely sometimes in the last 4 years. So Afshin Olamai has spent a lot of time doing the runway auditing. This is just to show you an example of what happens here. This is BDL Airport, and you can see that this is runway exit Victor. So this is the new runway exit, and this is the old runway exit, right? In the old days, we used to build this center line. I guess it was closer to the 250-foot radius, but now the radii is much more limited here. So that actually affects the performance on the runway. So the benefit of having the new data for over 4 new years, from 2017 to 2020, is the fact that now we can actually have a more up-to-date information on 3,500 and plus, is really more than 3,500 runway exits that have been audited. So where we have all the geometry design features. And this is very hard data to collect, but it's necessary because, again, when we are trying to understand what airplanes go into specific exits, we have really no choice, but we have to create those traps, that I mentioned before, these little rectangular traps, to be able to identify what airplanes are exiting and what are the typical exit speeds for those. So this is, again, something that we are going to be able to do. We have already an updated database, already is available. And again, we will have new airplanes there. That would be a good addition, we think, to both landing database as well as the model. Finally, we provided last year some new guidance, I guess, to the FAA to replace some of these cumulative utilization percentages. It actually was this year, I think in March, but we generated some of these graphs back last year as well. And the idea here is that using the runway exit model, we can run the model by putting artificially a large number of exits, runway exits, and then seeing what is the cumulative density function of the airplanes able to exit at a given location of the runway. And we have done this for all classes of vehicles. This is an example here for AAC. This is AACC. So these will be airplanes that have approach speed between 121 and 141 knots. and then we can do the same thing for Class D. We have done it for Class B and Class A as well. And notice that these design curves can also be presented as a function of pressure altitude if necessary, so that we can, give the designer that doesn't want to run the model what is a very typical location where you will be able to get a certain percentage of the population of this class of aircraft out there. In this case, this is for right angle exits, but we have also done this as well for acute angle exits. So this was part of the story that we wanted to tell you that you can do with the model. And finally, I would like to conclude here by saying that if you have any questions or ideas about the tools presented here, you can speak to me or you can send us email. Nick is the guru of how to integrate these models, and I'm sure he or myself will be very happy to hear your comments. So I'm gonna stop here because we obviously want to give some time here to have some discussion about what you guys think we should do. Andy is saying filter out cargo may help. So you don't want to see cargo airplanes? We don't have, well, we have MD-11s there and MD-10s and things like that. Is there any particular reason filtering out cargo? I'm curious. And why did you say that?
Boxes don't normally complain if you land hard, long, or fast, or brake hard on the runway. Also, you would be using an exit that heads towards the terminals. You use a different exit that heads towards a cargo facility in the opposite direction.
Right. You are right. I mean, maybe one potential recommended practice here is that people can run the model just isolating those cargo airplanes, and then you can design the locations to the cargo complexes, right? But I mean, you raise a valid point. Right now, we do have some cargo airplanes in the model, but I mean, the usual suspects, like MD-11s, MD-10s, a few others maybe that are out there. I noticed that one of the new airplanes was also going to be the Casa Nurtani, the 235, but I mean, I don't know to what extent that airplane operates much in the NAS, but that's kind of a military or cargo airplane. But anyway, I would like to hear what ideas you guys have about this, and maybe we can take the remaining of this time to start hearing from people. I mean, this is part of what we would like to do. We would like to do maybe 3 or 4 of these, actually 4 of these seminars, to hear ideas from folks who are out there using these tools, ways to improve them, etc. So I'll stop here and let you guys talk about it, okay?
Hey, Tony, this is Ken. One thought, I was thinking about Andy's comment, and Andy, thanks for that. Part of, I think, where the motivational algorithm will really go is essentially linking a given, type or grouping of operation to where it's going on the airport, and thus its motivation for braking more aggressively or less so. And it certainly you can see linking that into a cargo, the cargo ramp on the airport, for example. So I think that's part of. I think what you're asking for is that kind of linkage depending on where they're going to the airport. I think the other part is maybe it's not so much filtering out cargo, but treating cargo as a separate query just to see if there's a different performance that's coming with that. Is that a fair restatement of your question?
Andy, can you hear us?
Yeah, sorry, Ken. What was the last end of that question?
Yeah, so I think you say filter out cargo, but I think what you really mean is quantify cargo separately. In
Yeah, so I mean, in the landing event database as well as in the model, apparently there's no landings of this kind of this class of airplanes. Maybe there's a few, but you can always go and filter by, let me go to runway 8L and see if I can pick one particular airplane that may be potentially cargo, is right? So let me go to the MD class of vehicles. And you can always filter those out. I mean, you can always do the queries, and if the application finds MD-11s landing on these, because I guess the cargo complex in Atlanta is on the north side, so here you can see how the cargo operations are actually happening, right? So it found all of these UPS and FedEx MD-11s that are landing there, and you see all of the statistics. So technically, you can always do the query. I mean, I can just query here MD-11s, and then I can be presented with whatever number of operations happen for those 2 years. Now, this is in the landing event database. In the model, in the Redim model, when you run your scenario, if you wanted to, let's say, identify a new type of runway exit for that cargo operation, you can just select the MD-11. You don't have to run with any of these other airplanes. Is that you have 290 airplanes to pick from, so you can just isolate your analysis to one particular cargo airplane, and then the model will be able to tell you potentially what would be the correct exits for that operation. So I think that the easy way is in the landing event database, you can just refine the query to one airplane or a few airplanes. And then here you can just select the cargo planes and do your analysis for the optimization or to see what sort of benefit you may get out of that run, just purely with cargo airplanes. Um, so let me go back here quickly. And anybody else has any uh, comments that they would like to make or potential improvements?
Tony, this is Tony Chiori following up on Anne comment. Would you be able to filter by airline carrier?
Um,
Also, did they break in order to need an exit to have a shorter exit back to the terminal?
I think, let me see if we can go to in the landing event database, uh, we go
Yeah, in
here.
the landing database, we can I can add a carrier
Mhm.
filter. Right now, you can't do that.
Right. You can only sort, but you cannot filter by airline. But Nick, as Nick is saying, we could add, and I'm taking notes here, so as you guys speak, we can add a filter or a pre-made filter to filter out specific airline, for example. That would be relatively easy to do. Here, right now in this, you can actually sort, which in some way accomplishes partially what you want to do, but it doesn't do everything because you can filter by flight ID, and I mean you could just either deselect all or select the ones that are important. But in this case, we have the MD-11s. But yeah, I mean we could add another filter here in this tab to be able to filter by airline, and that will probably accomplish what you want.
Well, I think the idea is to be able to get the distributions also by carrier on a specific runway.
Right.
So it's not just the window within the other.
Oh, that's right. That's right, Nick. So I guess part of the story here, if we wanted to get, let's say, going to that runway eight left, and we wanted to get the distributions, let's say, for a given airplane, just like we did for the cargo airplane, the MD-11. Here we can say, go ahead and query the MD-11, and oops, I'm scrolling too fast. So MD-11, and then we would like to see the CDF of the aircraft speed profile, and then we can see whether or not, obviously this may be one of them, but the deceleration is probably another important characteristic that maybe people want to see. So Again, I'm just going to go to the same runway and do a distribution for that class of aircraft, for the MD-11, just to see whether or not they are, or we can just pick the DC-10 since it's there, and just do the query as well. It looks like it didn't find any DC-10, so we know that there is MD-11, so maybe I should stick to the MD-11 unless there's something incorrect with the database. What am I doing here wrong? It says 8 left. Isn't that the runway that we were using by aircraft? So maybe we find a bug here or something. Let's try with another airplane that is, yeah, it looks like maybe it couldn't find many of those to make a distribution. So, but anyway, we will, yeah, I think it's easy to be able to identify that by airline or by, right now you will be able to do it by exit as well. I think my computer is probably having some issue because I have a lot of applications open and it's probably uh, getting tired here. So I think I may have to. This normally should give you a CDF for runway 8LL, but I think that my memory in my computer, I have applications running because I'm recording this seminar, and I also have the parallels running, and I have a lot of other things running simultaneously. So it looks like my computer is giving me a hard time here, but you should be able to get those distributions, and we will add a few more filters on that. Anybody else has comments or ideas? Again, you don't have to give it to them to us right now, but you have our email addresses here, and if you come, after you perhaps use the tools, if you think about a great idea that perhaps in your application may help you and it could help others, we can start making a list. And we plan to make a list of ideas, and then in consultation with the FAA, we will probably say these are the things that we are going to focus on, in the next few months. So right now, where we are in the process, we have processed phase 1 of the data for 43 airports, but we still have to process phase 2, which is identifying runway use and all of the metrics and parameters that we have in those velocity and acceleration profiles on the runway. So still a few more, couple of months to go before we can process all the data, but we're getting there for 43 new airports in 40 more years of data. So again, this is an open forum, so anybody has any comments or questions? I lost the chat window here. I don't know what happened. My computer is probably not, is giving me a hard time. I would like to be able to pick AC type and figure we need multiple runs. John, can you elaborate on that? I would like to be able to.
I'm sorry. I was just commenting on the previous comment. I'm really looking forward to the capability of being able to select what you just went through different motivational types. And what I was thinking when we were talking about the cargo conversation, the conversation was looking at a certain interior. It would also be good to be able to filter that by aircraft type as well.
Yeah.
It's based on the same lines, but really looking forward to that being added.
Okay, very good. Thanks for your comment. Okay, anybody else? Go ahead.
Matt, one thing I've run into is that the clusters themselves have biases based upon these motivational factors. The example I like to use is the 7,500-foot long cluster has that O'Hare runway with the exits at the end, and actually the second runway at O'Hare where there is motivation to go through an intersection, and so airplanes tend to roll out
I see. That's a very good comment, and I think that that is a potential issue, as you mentioned. So I was looking here at the runway for Chicago that you mentioned, but also, for example, if we look at that runway, 7,500 feet, in that cluster, cluster 16, there are 12 um, runway ends. Actually,
And
so
6 of them are from O'Hare with long rolls. And that's my problem.
yeah,
Even though you think there's 12, there's 6 of those ends are at O'Hare
right, right,
with that problem.
yeah,
So even though you think you have a lot, there's still these biases in the data.
yeah, that's true. Let me see, just to check here. So we may find out ways maybe to, we have thought about decoupling some of these things. I was trying to think here. The cluster is 16. So I'm just trying to see what sort of nominal deceleration behavior we're actually seeing in cluster 16. So yeah, we are getting a fairly, this is one of those anomalies that you mentioned, because cluster 16, since these guys are arranged by runway length, we would expect right now that this deceleration rate be probably closer. Right now this seems to be an anomaly, and maybe, as you said, is probably biased because of that cluster has most of these runways do have only exits towards the end. So that's a good observation. So I think that could be addressed as follows. With the motivational factor, certainly that could be changed, because then if the user specifies motivational factor, then that will start migrating this kernel distribution to others potentially. But it will be kind of nice. We have to investigate if there are ways to try to decouple this so that we don't see this kind of anomaly where a cluster is only driven by few runways that are out there that have this bias that you mentioned. That's a great observation, really.
So we may try to revisit. Initially, we were trying to cluster by runway length and number of exits and so on, and maybe, and then we ended up just doing by runway length. And maybe what we need to do is try to cluster by runway length, and some parameters are indicating that there's only exits at the end or something like that. And maybe that would split certain runway lengths off into
Yeah,
reasonable clusters.
yeah, and we try several ways to try to cluster these, not only by runway length, but we, as Nick mentioned, we also put as another parameter in the cluster to be the number of runway exits. And then we even tried being a little bit more selective and saying, well, it's not only just the number of exits, but where the exits are located, right? So we would try to build a new clustering algorithm where we would use, um, we will try to build this based on the exits that are, for example, for an Airbus A320, that are feasible for that class of aircraft, so that we could make the cluster a little bit more, direct the cluster towards the more nominal behavior. So I think that with more data, we may actually attempt to do that, and then maybe the model will be more aware of that, because certainly if the cluster is biased because there's all these runways have only exits at the end, that's a problem. I agree. So we are going to try a few. Yeah, go ahead.
Just another thought on that idea. You have so much data here on the performance of the airplanes themselves. Maybe you build a cluster that's more based, and you give the user a choice. Do I use the observed clusters, or do I use something what I'll call a modeled cluster, where you show it with the graphs where you have regressed. You created
That's a very good
And the
suggestion.
problem with that,
Yeah.
is that you would have to then call us to reprocess all the data for that specific cluster, and we put it in the model.
Understood. I'm not saying it's an easy thing to do, but it may be a long-term research goal that we do create a mode. Because that's in fact how Redim 2 used to run.
Right.
It's much more this idealistic mode. And I love the idea of, and don't get me wrong, it's wonderful that we're tying this to real data and it really improves the credibility of the model. And so now what we're doing is struggling to get the biases of the data out of the model. And maybe the idea may be that we use the data that we have to create a more robust general model, and we give the model the user a choice which way they want to run the model.
Mm-hmm.
Yeah, just thinking out loud a little bit, Matt, and I appreciate that input. You know, I think what you're really asking for, is that just kind of thinking through this is not necessarily totally one or the other, but have one that I think, as you said, it breaks from the data just a bit and gets a bit more into the modeling, but doesn't go purely optimistic. Because pure optimism can have its own biases and shortcomings. But I think what you're looking for is something that's a bit of a hybrid. And I mean, I'll say that I'll give you the mic back in a minute, let you comment on that. And then, but the other thing that I think I'm wondering about, or that we've been thinking about, and this gets into Bob Zimmermer had this question too. You know, what about other airports? And part of this is we started with the data that we have available, the 1 second position updates, which is going back to the data that's currently in Redim 3. That's I think it was 2016 2017 as DX data, which is a subset of 35 or so of the airports. And what we're doing now with adding data to the tool is going up, including the 43 airports that include that ASSC upgrade. And then, we expect to be able to get into a point eventually where we're reporting in the ADSB data, which allows us to cover some smaller airports too. And so, in theory, over time, that gives us clusters that are less dependent upon specific runway environments like, what you highlighted in Chicago. So I think it's kind of a two-part thing to think about. One is, there's an advantage to more data, and two is, what you seem to be seeking is the ability to run the tool in more of a balanced mode. Back to you, Matt.
I think you hit the nail on the head. I'm not sure I have anything to add. This is not an easy problem to solve. And we have workarounds at this point that we're using. And we're acknowledging the workarounds and the analyses that we do. And so this is not necessarily a short-term problem to fix.
Yeah, but I mean, Matt, you raise a very important point, which is in the design of Redim 2.1, we tried to be very normative. I mean, normative because obviously we did not have the wealth of data, and we wanted to bound the distributions in the Monte Carlo simulation model. We assume, we truncate them to 2.5 sigma from the observed behavior from the video. So the model was a lot more nominally. I think the output was a lot more nominal, what you see here. And but I think we have to think about that because, if we are going to remove some of the bias, there might be ways to do it. I mean, when we see this kind of situation where only a few runways are driving the whole behavior of the cluster. So I think that either by looking at the data or by perhaps programming some way to have a very normative behavior like in Redim 2.1, that could be entirely possible too, because with dotted lines like this, we could still drive a Monte Carlo simulation in the model that in some way bypasses the kernel distribution and just uses this very normative behavior. I mean, it would be more like a quick evaluation, but who knows? Maybe that's useful to airport designers. And you guys are using the model, so we certainly value all your input here. Let me see. Do we have other comments that the audience would like to do? Glenn talks about the ICAO capability to allow two aircraft on the runway at the same time. There is a move to reduce 2 to 2 nautical miles on runways. Um, yeah, so ROT will be more important, I think, in those. So we agree with that, Glenn. And we hope that maybe the model may be able to answer some questions um, about that kind of future work that ICAO or the FAA is thinking about it.
Yeah, I'll make a couple points there, and appreciate the comment. We actually had a chat yesterday with flight standards on some of this work, and kind of thinking through future applications and a bit of some synchronization work we expect to do probably this summer just to compare data and notes, because we'd certainly ultimately like to be able to run those 2-mile arrival separations if that's a capability that's approved. We'd like to be able to run that in the tool and understand if there's an infrastructure need that's necessary to enable that capability. So that's definitely something we're tracking. And I think your comment on break to vacate, auto land, etc., is also really important. My sense is, and Tony and Nick can elaborate on this, as those capabilities become more common and widespread in the system, then those capabilities and other capabilities generally, then we're going to start to hopefully see that in the observed data. And as we, in future years bring in new observed data, that will become available for the tool. And then I think that brings about probably another question, which is, at what point do we bend the tool to favor that newer data and not favor as much some of the older data with prior procedures? But that's a question for another time.
Yeah, and the break to vacate, it may already be in some of the new data, especially for airplanes like Airbus A380, for example. I don't know exactly when that system was certified, but I suspect that the 2015, 2016 data for Airbus A380s may not include break to vacate. So it would be interesting to compare the distributions before and after, assuming that the break to vacate was actually certified and is available now in the new data. So it will be interesting to see if the runway occupancy times have been reduced substantially. And but I mean, my own personal observation is even with break to vacate, the 380, for example, landing at Los Angeles still take a long time to get out of the runway because of the sheer size of the wingspan. So we still may be able to see differences there, but we could still see runway occupancy time still taking alpha alpha or bravo bravo 24 right, up to typically 75 to 80 seconds. That's what we have seen there. But that's a great story that we may be able to answer with the new data. Yeah, that also may introduce some bias, as Glenn is mentioning in the chat room as well. Depends on what the pilot, I guess, programs. But those capabilities are now available in the 350 and other Airbus aircraft types. So we should be able to see that in the new data, because those are the new airplanes that we are going to be able to see when we process all the new data as well. And probably all of these guys now may have break to vacate. I think we have to go back and examine if that's the case.
Another reason to filter the data by carrier because different carriers have different procedures.
That's correct.
What they're allowed to do.
Yeah, that's a great point.
Yeah, that is well said, man.
Yeah. Well, it looks like.
Of course, it's its own challenge. It's its own challenge as well because those things can change over time. So if you optimize the exit for one airline, one procedure, and things change, then there's always the endless rabbit hole aspect of it. But it certainly makes sense to be able to consider that specifically. Just given the variation by airline for the same aircraft type. So thanks, Matt.
Yeah, I also would like to remind everybody that this presentation is going to be available in the Air Transportation Lab website. So if you go to that, we should be able to see that. And Nick, we will be able to post that very shortly, is that?
The presentation is already there.
Oh, okay. The presentation is already there. So the same address that we gave you at the beginning of this presentation, if you go to this website here, you should be able to bring the presentation in PDF form. I think it's like 26 megabytes reduced file size. But we will also make available the webinar, the recording, so that you can go back and explore this. And again, we appreciate all your feedback, all your input. And if you have some ideas, please feel free to send a note to me or to Nick, okay, about this. I mean, I know some of you may have I can stay here beyond 3, I have no problem. But if you need to log out, I understand. We timed this for 2 hours. Ken, do you have any closing remarks or anything you want to say?
One thing is, Amy and Tony, I think we see your comments, and I'll loop back with you over email on that to include Tony as well. So thanks for those. But overall, thanks everyone for your participation today. This is we're looking to do this from time to time, briefly as we get into the motivational algorithms and some of the data updates. But we very, very much love the feedback on different ways to tweak and adjust the tool, be able to query the data. Appreciate the commentary on clustering and more airline specific queries. So thanks everyone for that, and that's exactly the kind of feedback we're looking for, and we look forward to working with you all in the future.
Very good. Thank you, Ken, so much. And again, just a quick reminder that if you go to that website, Nick has already posted the presentation that we made today, and the video will probably be posted tomorrow once I process the video, okay? Thanks, everybody, and you guys have a great afternoon, and so long, okay? Bye-bye.